Gnanam Paramam Dheyam. Knowledge is supreme.
So now let us look at what are the different types of models which can be written for chemical processes, and we are actually interested in developing models which will be eventually used for process control. So there are three types of dynamic models which can be written depending on how much information about the process is available and how much accuracy you require from each of those models. So the first type of models are known as first principle models. We will also call them as white box models. So as the name suggests, they are based on the first principles or principles of physics, chemistry and biology. So you can also call them as fundamental models based on the actual theory of the system, and they will deal with conservation laws. So you know that in any process mass is conserved, energy is conserved. So when you write these balance equations or when you write first principle dynamic models, you will try to write on the fact that these conservation laws are valid on that particular system, and in addition to that you also have constitutive relations. So you have conservation laws which will be conservation of mass, conservation of energy, and you can also have constitutive relationships which are not captured directly by conservation laws, but by some other either experimental equations or fundamental equations like kinetic rate clause, or mass transfer relations. Heat transfer law. It can be ideal gas law. Can be equilibrium relations. So when you combine all these theoretical aspects of that particular process and come up with a dynamic model of that particular system, it is known as a first principle dynamic model. So we will take few examples and then try to find out or try to write down first principle dynamic models for some of these simple systems. So the first example we are going to consider is that liquid storage tank. If we have to write the first principle dynamic model, we will start with the conservation equation. Now for this system there are no energetic effects. So all we need to write down an equation is for mass conservation. So if I say the volume of the tank is V and area of the tank is A, density of the material is rho, then I can write down the equation rate of accumulation of mass inside this system is equal to rate of mass input minus rate of mass output, and as there are no reactions, there is no consumption of mass or there is no generation of mass. So, rate of accumulation of mass in this system will be time derivative of mass of the system, which will be rho times V, which is equal to rate of mass input, which is rho times F in, minus rate of mass output, which is rho times F out. And if we assume that density is constant, we can write down dV by dt is equal to F in minus F out. And if we try to convert this volume into height, we can write down A times dH by dt is equal to F in minus F out. So, this is our first principle dynamic model of the surge tank, or the first pass at writing down the first principle dynamic model. Now, here the time derivative comes for height. So, H is known as the state of the system, because it tells me what is the status of this particular system. If the height is very close to the overflow condition, then the status of the tank is it is going to overflow, or if the height is very close to 0, the status is it is going to go dry. So, the variable which is typically written as a time derivative will give you status of the system, and therefore, it is known as a state variable. So, for this particular example, H is a state variable, it gives me the state of the system, and extension of that is if this variable remains constant, then we call it as a steady state, and that is when we have a steady state, this dH by dt goes to 0, and therefore, 0 equal to F in minus F out or F in equal to F out becomes your steady state condition. So, steady state model can always be obtained from a first principle dynamic model by simply equating the time derivative of the state variable to 0. Now, in this same example, we can also add constitutive relationships. A very common assumption is that the outlet flow rate is proportional to the height inside the tank, and which is very intuitive, because if you look at this particular figure, if I have a lot of material inside the tank, obviously the flow out of that tank will be very large, as compared to if there is very little liquid in the tank, the outlet flow rate will be small. So, it is quite a common assumption to it is quite common to assume that the outlet flow rate is proportional to height, and we can write F out is equal to H over R, where R is known as the resistance of the wall. So, if I use this constitutive relationship, then my first principle dynamic model becomes dH over dt is equal to F in minus H over R. Now, if I want to be more rigorous, then F out is not proportional to H, which is actually proportional to the square root of the height, and F out can be written as alpha times square root of h, where alpha is the wall constant. In such a case, the same dynamic model can be written more accurately as dH over dt is equal to F in minus alpha times root h. So, depending on what constitutive relationship I am writing, the final form of the first principle dynamic model might change, but a first principle dynamic model will always be written as a conservation equation followed by the constitutive relationships, which may be some additional physical law, or it may be some experimental or correlation or relationship. Let us now look at another example, this time the one which has significant energetic effects. So, we will consider an example of stirred tank heater. So, similar to the previous example, there is a tank, fluid comes in at inlet flow rate and it leaves at certain flow rate. So, let us for the simplicity assume that the inlet and outlet flow rate are equal, so that the volume inside this tank remains constant. The inlet comes in at a temperature of Ti, heat is provided to this tank at the rate Q, and because of that the material inside the tank, which is of amount V, gets heated to a temperature of T, and the stream leaving the tank also leaves at the temperature of T. So, for this example, as I said, the material balance automatically gets satisfied because the amount of the material coming in is equal to the amount of material that is going out. So, we do not need to consider the conservation equation for mass. So, we will start with conservation of energy. Now, here let me point out that energy would consist of thermal energy, maybe potential energy, kinetic energy. In chemical engineering systems, most of the times the potential and kinetic energy components are very insignificant compared to thermal energy or enthalpy. So, most of the time, even though we talk about conservation of energy and writing energy balance, we are mostly implying that we are trying to write an enthalpy balance. So, let us try to write enthalpy balance for this particular system, which will be rate of input minus rate of output plus rate of generation minus rate of consumption is equal to rate of change of content. So, rate of input of energy will be the enthalpy coming in through this input stream, which will be F in times rho Cp Ti minus T reference, where T ref is the reference temperature for enthalpy calculation, and there is one more input from this external source Q. Rate of output will be written for this particular stream, which will be F in rho Cp T minus T ref. There is no generation or consumption of energy inside the system, so which will be equal to the rate of change of enthalpy content of this tank, which will be V times rho Cp times T minus T ref. So, let us now try to simplify this. we can assume that the density and heat capacity of this particular stream remains constant as a function of temperature. So, we can assume rho Cp to be constant as a function of temperature. This is an assumption. So, we can simplify the previous equation as Fin times rho Cp Ti minus T plus Q is equal to V rho Cp dt over T. So, this becomes a dynamic equation for the stirred tank heater. So, this is the dynamic equation for this stirred tank heater. So, it gives the relationship between input, which is Q, to the output, which is the temperature inside the tank or temperature leaving the tank. It also gives the relationship between the potential disturbance, which is Ti, and the output T as a function of time. So, it satisfies the definition of dynamic model. Now, at this point we have not specified how that heat is entering into the system. It may be that there is a jacket around the stirred tank heater where steam is injected, and then that hot steam will provide heat to the tank. So, in that case we can write some constitutive equations. In this case we can write rate of heat transfer equation, which will tell me that rate of heat input will be UA times T in the jacket minus T of the tank. So, using this equation we can refine our dynamic model as V rho Cp dt over dt is equal to Fin rho Cp Ti minus T plus UA Tj minus T. So, even this can be used as a dynamic equation for this system, which gives the relationship between now jacket temperature and the output temperature as a function of time. So, we have seen two examples of first principle dynamic models. Now, let us look at the advantages of first principle dynamic models. So, the first advantage is that it gives a physical insight into the system. As it is built based on physical principles, it gives you how that system is going to behave under different sets of conditions. It also gives you what are the inherent parameters or which needs to be considered in order to understand the response of the process. And the second advantage is it has wide range of applicability. As minimum assumptions are made and mostly physical laws are followed, these first principle dynamic models would be applicable over a wide range of operating conditions. Now, having said that, let us now look at what are the limitations of first principle models. And the major limitation of a first principle model is that it may be time consuming, to develop these equations. We looked at very simple examples, so that is why it was not evident that these can be difficult, but if you look at real chemical processes where multiple unit operations are interconnected and the number of variables may go into hundreds, In that case, writing dynamic equations for each and every process variable may be cumbersome, and it also gives rise to an additional limitation that many of the parameters which are part of the model may not be readily available. So, non-availability of model parameters, these may be mass transfer coefficient, reaction kinetics, or vapor liquid equilibrium coefficients. So, all the physical details or some of the parameters which are required in the model may not always be readily available, and in that case applicability of first principle dynamic model gets restricted. And lastly, especially from the context of this course, we are interested in using these models for controller design, and in that case if the model gets really complicated, we will see later on that it will be very difficult to incorporate into the design of a control system. We typically tend to go for a simplistic model which can capture the response of a process. So, therefore, it may be difficult to integrate into controller design. Thank you.